Uh, yeah, it is now recorded. Or shall I make a live stream on Facebook, sir?
Oh, well,
Uh,
I'm not in Facebook. I don't know.
okay, so no bother. Okay, let me continue. Okay, so today we have our talk on intervention in a building for energy efficiency, ground stories from Professor Dr. Wolfgang. On this program, I, on behalf of graduate student of energy efficient building design, organizer of this event, would like to welcome and extend my warm wishes to all our attendees, and I would like to express my gratitude to our speaker, who is here to share his valuable expertise and his ground stories in the intervention in a building for energy efficiency. My name is Chitis Pandit. I am enrolled in master degree in energy efficient building design in Kathmandu University in 2018. I highly valued this opportunity to moderate this event. Well, about the detail you are posted with, our speaker will have 30 to 35 minutes time to discuss, followed by 15-minute question answer session. And meanwhile, our attendees, our participant can post your queries into the chat box, which we will further address in the question answer session. Okay, this session is recorded for the further use. Now, without delay, to set up the stage for the opening remarks and welcome remarks, I would like to invite our Associate Dean of School of Engineering, Professor Dr. Hari Prasad Neopane. Well, knowing him, he holds an PhD degree and expertise in the fluid engineering from Norwegian University of Science and Technology. Besides that, he had been numerous research on related to hydraulics, hydrology, and turbine-related hydropower program. So, without any delay, I'd like to hand over this mic to Professor Dr. Hari Prasad Neopane, sir, for his welcome remarks. Sir, the floor is yours.
Okay, thank you, Chidit. Very good morning to all of you. Thank you very much for inviting me in this event. In fact, this is a very good initiation from our graduate students. I know that this is the 3 days event, and we are in the day 3. And one of the renowned professor in this field, Professor Wolfgang, we were connected. We worked together since 2015 in one of the project, and the outcome of this project is this master program in our university. So it is our pleasure to have Professor Wolfgang in this session, and we are very much interested to learn what you are doing and your experience, and I hope that your lecture in this particular topic that will add very much value to our students and our curriculum. For your kind information, the curriculum we developed from that particular project, based upon that curriculum, one of the subject we in the 3rd semester we call the graduate seminar subject. From that subject, students are this event. So in this regards, I really thank from my bottom of heart to our students and the course instructor. Because of that, we are together here in the day 1 and day 2 also. Renowned speaker from different part of the world, they delivered the lecture, and today we are also expecting the very good lecture from one of our colleagues. We were very familiar since 2015, and we know each other. So it is our pleasure to have you, Professor Wolfgang, over here. And without further delay, I again welcome you all in this event. And this is very good initiation from our students, and I hope it will continue in the days to come. And this is the way this COVID impact us in positive direction, so that we can have an interaction even in the virtual mode. But in order to learn the things, this is quite good. So thank you all, and welcome you all, and especially Professor Wolfgang. Thank you very much for accepting our students' invitation, so that we have you today. And I'm really looking forward for your presentation. Thank you all.
Thank you, Hari sir, for your wonderful welcome remarks. Now, without further ado, I'd like to turn over this mic to our speaker, Professor Dr. Wolfgang Streicher. Knowing to him, Dr. Wolfgang Streicher is a professor in Institute of Structural Engineering and Material Science University of Innsbruck in Austria. Yeah, and then he has done his bachelor degree in mechanical engineering at Graz University in Austria, along
Austria.
with Austria, sir.
Austria. Yeah, not
No,
Australia.
no
So
kangaroos.
Austria,
It's completely different country.
the pronunciation is different, like Austria.
Austria.
Okay. Yeah. Yes.
don't, don't worry, it's okay.
He had received his PhD at Graz University of Technology in 1986 to 1991. He has led the leader among of working group of energy efficient building at the Institute of Thermal Engineering, Graz University of Technology, since 2000 to 2010. And since 2009, he is a professor in the energy efficient building and renewable energy at the University of Innsbruck, Austria. Well, Wolfgang Streicher is currently ISES, International Solar Energy Society, Europe President. He teaches building services, engineering, HVAC, heat pump, tube hydraulics, modeling, thermodynamics, energy, and ecology. Beside all these his professional experience, his current research focus is on development of cost and energy efficient system solution for HVAC system, including renewable energy demand of cities using GIS and bottom-up approaches, hydraulic of complex tube network, energy efficient system for cities and energetic scenarios to reach the 2050 climatic goal. He had worked in this field since more than 30 years, has published numerous funded papers in reviewed international journal and conference, and he is member of several national standardized committee. Moreover, he has coordinated many projects of Austrian institution as well as the European Commission and international agency. With this all short biography, I'd like to hand over this mic for Professor Dr. Wolfgang Streicher to drop his remarks. Sir, the floor is yours.
So, thank you very much for these very kind words, and I'm really happy that I'm allowed to speak here and that you invited me. I will try to share my screen, or at least my. So, is it possible you can see my screen?
Yes, sir, we're being you.
Okay, the slides screen. Okay. Well, you already said we had a very nice project in Nepal and also in Bhutan, and I'm really happy that this master studies are still ongoing and that you carry on with that matter. So the project was really a success, and this was, of course, due to all the colleagues in Kathmandu University in Nepal. So Hari Neopane, thanks a lot for keeping all this, and it was really a pleasure staying with you, and hopefully I can be in Nepal once again after the crisis is over. Okay, so thanks a lot again, and I'm really happy to make this. Well, about energy efficient buildings. This is something I carry with me since 30 or 40 years. I'm a studied mechanical engineer, as was said before, and also already in my studies, I was dealing with biomass and heat pumps and solar thermal systems. And then we found more and more that, well, if the buildings would look better, we would need far less from all these renewables to fulfill the demand of the building. So I was switching more and more to the building itself. So make the building efficient means make it more clever, make it more smart. So you get the same result, the same conditioned room, cooled or heated or whatever, with far less energy input. And I think that's a clever solution. That's what I learned in mechanical engineering, is as simpler and as less input you need for a solution, the more clever it is. So we should think about not only energy efficient building, but clever and smart buildings. And smart buildings does not mean that you have a lot of electronics in there. Smart buildings, that mean that you have a smart knowledge of how a building works, how the structure can be used, how the windows can be used, how insulation is being used to make it clever and reduce not only, let's say, the energy input and the CO2 emissions with that, but also reduce the operating costs. That is another point which is, at least in my country or all Europe, I don't know how it is in Nepal, which is a bit strange on buildings. So normally you look for buildings only, well, how much do they cost? But you're thinking about investment costs and not operating costs. And then you make a debt by the bank, and then you pay back monthly the credit by the bank, and you pay monthly the operating costs. And why are one of them counting and the others not? I still don't understand that. But that's the whole thing behind energy efficient buildings. It is make the building clever and use as little energy or costs for run that building. And this, I want to show a bit the principles here in my lecture, how they could be achieved. Okay, so let me have a laser pointer here. Okay, I don't know why this is doubling. No idea. Sorry, this is not too good. May take another one. May switch it off again. Okay, no, I cannot use really. I try to use the laser pointer, so it's one of them is working. Okay, so if you want to make an energy efficient building, well, you have to have an, let's say, integrated approach. If you have a low cost building and a low energy demand building. So first you should see, well, that's clear, is it the right building at the right place? That should be the future owner and the architect, and maybe the spatial planner should do together if it's the right building and the right size and the right place and so on. And then when you start making the building, then, well, if you have an architectural competition or if you have do the planning yourself, whatever, then you draw the building somehow. And then in the first sketch of the building, you already fix about 40% of operating costs. That means your how you place the building, how many windows you put in there, how in which direction the windows look, how you make overhangs for the windows or not. This is already has a very strong impact on the operating costs and the energy demand. So first, make the building itself clever. And then when and you can think about also having the shading systems in there, especially in the hot summers of Nepal, and when it's also humid out there. So you want to keep the sun out in summer, and in winter you want to heat the building. So insulation is also a matter where you can reduce the space heat demand and have good windows in there and make the building a bit tighter as maybe normally. Then you can reduce by far the heating demand, and this is also operating cost. So this is the building itself. And once you have done that, then you can think about, well, how do I get the heat and the cold in there in the building? No, you don't get cold in the building, you get heat out of the building. That's second law of thermodynamics. But this is just a remark. So you think about the system, the heat delivery system into the room. So that could be a single stove, there could be radiators, that could be, in my country, very well thought about floor heating system, even a ceiling heating system and ceiling cooling systems are coming more and more into use. So make a double use of the same appliance for heating and cooling. So don't buy two separate things. I mean, in your country, probably it's split climate units, which do the same thing, heating and cooling, but for every room separately. But as less the building needs, as less you have to run these things, and as smaller you can design them. So you can save even investment cost and operating cost if once the building has been designed in the right way. And then the very last question is about where does the energy is coming from. Is it PV on the building, you get it out from the grid, or you take oil or gas, or hopefully not coal, not too much coal anymore. In my country now, it's even forbidden to use new oil burners because we want to get closer to our climate goals. And we're discussing even phasing out natural gas in the building. So just, well, what's remaining then? And then it's only a heat pump system, or your split unit is also a heat pump system, and driven hopefully by electricity from hydropower and PV and wind. And here, I mean, that's also the situation in Nepal, that you have quite some possibilities to have the electricity run by renewables. Okay, so this is an integrated planning step, but what is very crucial is that you have these feedback loops. So it's possible to, when you find, well, in the HVAC system, well, that's, if people here have an idea, well, if the shading system would be better, we could reduce the cooling demand, then there must be a feedback to the architect in the first step and said, well, okay, let's make the building a bit better, then we can reduce our efforts here. But the question is, who should do that? Is it done? I mean, the people that want to save heating, ventilation, air conditioning system, it's not in their interest to reduce their income. So why should they say, well, if you make the building better, we can sell less? So that's a problem. So they will never suggest to make the building better. They are happy with bad buildings because then they can sell more. So there must be a kind of general planner behind, having his fingers in everything and try to optimize the whole building. If you let this done by the single producers here, by the civil engineers, by the HVAC guys, and then the people that want to sell PV, they all want to sell as much as possible. So you will never get an optimized building. This is a tricky situation we face in the building sector, and probably it's quite similar in Nepal here. So it is not too easy to get this nice light become a reality. Okay, but where do we get the biggest mistakes? The biggest mistakes in buildings, so this is statistics of a large building company, Bilfinger Berger, that's a worldwide acting company. And they said, well, the biggest share of mistakes is planning mistakes. So that's another issue, that people don't give enough money and time to do proper planning. And if once the planning is wrong, then you run into a huge amount of costs, because then the building is built maybe wrong, you have even maybe high investment costs, or it's not even functioning, or you boost the operating cost. So this is one very big thing. Take enough time for planning, but then you have to be sure that the planning is done in a good way. And the next biggest thing is missing sensibility during construction. That means who is working on site. Normally the cheapest workers are on site, and because nobody wants to pay more money than the cheapest ones. But the cheapest ones, they are of course not educated. They don't know what they're doing. They just do what they've been told to do, and they have to do it as fast as possible. So they have to make how many square meters of wall per hour and so on to get it cheaply done. So they have not at all any sensibility what a building should look like, and not even more what an energy efficient building should look like. So again, we have a problem how to overcome that. Once you educate these people, you're one of the very good educated people here. But if you educate the people working on site, then they become too expensive, then they won't get the job anymore. So another dilemma which we find here, how to overcome it. And there is no real conclusion to that, how to overcome it. I mean, it's maybe just the people that built the building or that own the building later, they should be far more in favor of reducing operating costs and not just investment costs. And if you tell me, well, there's an investor, and the investor doesn't care about operating costs because he sells it anyway, but the final customer, the final end user, he has to pay the whole bill. And as long as the final customer is not demanding energy efficient buildings or low operating cost buildings, or even is able to put operating costs and investment costs together, nothing will change. But if the final customer is putting these two costs together, so operating costs for 20 years and investment costs, and calculate the whole sum, then we may get a different market. And if the market becomes different, then the investors will act different because they want to earn money. And if they get more money for a building that has less operating costs, they will do it. They will adapt very soon to the market. But the market has to reflect it. Oh, well, finally, our time is already running and I'm not really at my theme yet. So we'll speed up a bit, but this is a very crucial point in the way. So if you have, that's the timeline of construction and building use. And in the planning phase, well, you can do with very little cost, you can change a lot in the building, and you have a very high influenceability because the costs of changing something, changing a plan is far lower cost than changing on-site something. And once the building is built, when start being constructed, then costs are strongly increasing if you want to change anything. And if you want to change anything in the construction available already there, then you're more or less lost. So we have to put far more effort in the planning phase. Well, finally, how are the energy flows in a building? You should have learned that in your study. So we have lots of energy flows, and also the building is working according to first law of thermodynamics and second law of thermodynamics. So second law means you have an energy flow from high temperature to low temperature via the roofs, via the floor, via the walls, via the windows to the ambient, what we call transmission losses. Then we have the ventilation losses. You have to exchange the air in here to have acceptable air conditions in there. That means low CO2 content, not too high humidity, dust, odors, smellings, whatever, keep low. So you have to exchange the air. And if you take in air from the outside, you have to bring it to temperatures you want to have inside. For sure, you have internal gains here. You have people, you have cooking, you have lighting, whatever in here. Lighting has become small with LEDs, but nevertheless. Then you have, of course, the sun shining through the windows, heating up your house, which is nice to have in winter, but it's not too nice to have in summer because then you have to do cooling and a lot of operating costs again. Then you have two arrows here. This is the thermal mass. So if you have a higher temperature in the room than in the wall, then you have an energy flow inside the wall. And if the wall is hotter than the room, then you have a flow out. So how can this be done? Well, during the day when the sun is shining, in summer you heat up the room more and more, and then if it's hotter than the wall, then the heat starting flowing inside the wall. It's not heating up the whole wall. It's starting flowing inside in a transient heat transfer way. And at night, if you can open the windows or cool down the room, then the hot air the heat's coming out again from the wall into the room and hopefully is taken away. And with this, you can dampen the temperature variations in your room by far, because the density and the specific capacity of the wall is far higher than of the air. So every energy that is taken in here is not heating up the wall, or far less heating up the wall than heating up the air. So the air, every energy that is taken by the thermal mass is reducing heating up the air inside, and the other way around. So that's how we use thermal masses. Well, there can be also a transmission inside, and everything that is, well, if you make the balance of the whole thing, that is what we do in energy certificates over the year, or in heat demand calculations and so on. And what's left is to keep the whole room in a comfortable way, has to be done by heating and cooling system. Okay, so and we built, of course, for the people inside. So you learned also in your studies what is thermal comfort and comfort inside the room, what has to be kept there. So if you look on it on a graphical way, a lot of these losses, the UA delta T, that's the transmission losses, and the V dot rho Cp delta T, that's the ventilation losses. So the UA delta T goes from one media to another media via a wall. Always, if you have this situation, one media to another, you use the UA delta T. You use it also in heat exchangers. And if you heat up or cool down one media in the flow, then it's that formula here. Okay, both of them are depending on internal minus external temperature. And if it's cold outside, then you have to do heating. And the losses, they follow somehow a linear line, because that's a linear dependency. But on the other hand, so the colder it is, the higher become the losses. But on the other hand, you have the sun coming in, you have people working in there. So in real operation, you're working somewhere here. Well, that is changing all the time. So when the sun is out, you have less real demand to put in. If the sun is not there, you have no additional gain. So you have to cover all the losses, especially at night. When people are in there, then you get some internal gains and so on. So you operate somewhere here. And the missing part is the active heating you put in here. And the same, well, is about for cooling. If it's too hot outside, then you have to do cooling. If it's too humid, that's not in here, you also have to do dehumidification. And there is some part of the energy demand that is independent from ambient. So this is domestic hot water demand and household electricity demand. So it's not depending on it. But this is not a good building. A good building, at least in my climate, would look like that. In my climate in Innsbruck, we can do it. In Nepal, it's a bit tricky. Up in the mountain, it's possible that you say, well, I make the building in a way that I have no cooling demand at all. Well, how could that be done? How can I say, well, I don't need a split unit and the building will not heat up? And in winter, I can say, well, I insulate my building more, I reduce the losses, and insulating the building means the U value. Reducing the U value, so I reduce transmission losses. I could also reduce the ventilation losses by having a heating recovery, air heat recovery unit. So I have a heat exchanger when the cold air, in winter when the warm air is going out, it's heating up the cold air coming in. And in summer, the cool air coming out is pre-cooling the air coming in. So with air heat recovery units, that could be done, and even split units. No, split units is not possible, but small ventilation units will have more and more of these heat recovery units in there. Well, you see, they get the same heat demand, but with far less input. And if you insulate the building in winter, once the sun is shining and you have some windows in the right direction, you don't need heating at all when the sun is out. So the sun is heating your building. And only if nobody's there at night and thermal masses have given all their heat away, you have to start the active heating. So the internal and the external gains become far more important and do far more reduction in low energy efficient buildings and in high energy efficient buildings. Okay, well, we said about most of that. You can read it. We had these formulas. By the way, these formulas, you can also see them completely different. You can say, who is responsible for what of these figures here? So for the A, who is responsible for the A, for the area? Well, that's the architect. The architect is defining the design, and he defines all the areas of the ambient walls. Well, who is responsible for the U values? Well, that's the building physics guy or whoever. So who designs, well, how much insulation do we put in here? Who is responsible for T inside? Well, that's the final user. And who is responsible for T ambient? That's the climate. So we have 4 completely different groups or sources of these figures, and that makes it a bit tricky to make the calculations right, because you have to get the right figures. Well, you could do the same here, but this says the ventilation is the user or the technology behind. Well, this is air, and here again we have the user and the climate. Well, how to make energy efficient? We can start with the A. We can start with the ambient area. So if you have a volume of building, and you can place the volume in complete different shapes. And I know in your country you have these high towers with many stories on it, and if someone is marrying, your parents have to put another story on it to give the young family room. So this is already quite good, but if it's standing alone, you have still a lot of outer walls, and if you put it together and have it as a row house, then it becomes far smaller. But this is already quite good compared to a building like that, where you have far more outer surface. Well, U values in my country, you have upper limits of U values. So we have some building codes where you're not allowed to go higher than that, but these values are not very good. So we should have reduced them by far since a long time, but somehow it's not working, but I don't go into this detail. Well, you can build buildings with very, very low energy demands, and this you can do all around the world. It's not only this for our climate. So in my climate, space heating is the mainly demand of buildings, or old buildings, they use a lot of space heating, energy demand, and domestic hot water and household electricity. But then building codes became more and more strict. So nowadays, but that's a very old graph, we have, due to building codes for single family houses, about 40 to 50 kilowatt hours per square meter in year energy demand. But you can do far better. You can down to 15%, and that without too much additional cost. Because if you build a building, then it is not a big issue of costs if you put 5 or 20 centimeters insulation on the roof. I mean, if you just look for the cost of increasing the insulation, that is compared to the whole cost of the building, that's quite minor. In my country, it is sometimes nowadays even more expensive to buy 2-pane windows instead of 3-pane windows, because all the production lines of the companies producing windows, they're put to 3-pane windows, and if they had to change it back to 2-pane windows, which are worse in terms of U value, then sometimes you even have to pay additional costs. So nobody's doing 2-pane windows anymore in my country. Of course, heating is more important here. Well, the target criteria we had already for the whole system, make it as simple as possible, not as complicated. Everything you can spare is spared money, and it's spared operating costs and spared maintenance. So if you make a, well, what you find in literature is a smart building, is a building that has a lot of electronics in there, a lot of sensors, a lot of actuators and things like that too. And that, well, they say you can optimize your building and you can run it from your smartphone and whatever. But on the other hand, every sensor you have in there needs maintenance, and it breaks down after a while. And if it's not working, who is repairing it? And even before, even if it's working, who is programming the controller in the right way that it's really working? So my experience is the more electronics is in a building, the longer it takes, or until it may run, and it runs worse in the end than a simple building without all that stuff. So to my opinion, they just sell you a lot of stuff for nothing. The last thought on this is, if you, well, how long do you get spare parts for electronics? So if you have, I don't know, a cell phone like this here, how long do you get spare parts? Or if a car with electronic parts in there, how long do you get it? So for a car, you may get it for 10 years. For a cell phone, you don't get it at all. So you have to buy a new one. So how long did you get spare parts for electronics in buildings, and what is the lifetime of a building? So that means at least every 10, 15 years, you have to replace the whole system with all the costs again, and the additional costs taken out the old system. So coming back, make your building in itself smart. I have a saying that says only stupid buildings need artificial intelligence. So make the building itself intelligent. So that's the first point. The rest, I mean, we had already, but down here, there are also two very important items. The main thing is it has to work. We're building for the users, and the building should simply work. And if you achieve this, that's the highest goal. And if you do it even with low energy efficient and simplicity, then you're the genius. Okay, what are our building materials? Well, we have in my country, let's say, 3 main materials. We have the bricks, we have wooden construction, and we have concrete construction, where we don't have the pictures now. And well, how can we classify it? Well, the brick is always sold as we want to build massive buildings, but if you have a side look, a brick is not massive at all. And the only thermal mass we can use is this very, very tiny part here, where the heat can flow in and out. Why should the heat in 24 hours move further down here and go up here? So a brick is something very lightweight and has not really thermal mass, at least these types of bricks. The thicker here, this part becomes the bit more thermal mass you have, but it's not all the thermal mass here. And the interesting thing is that the wooden construction and the brick construction, they are very similar in their properties. It's completely different if you build with concrete. A concrete is a very good thermal mass that has no pores and nothing. And what we also say, it's better, I mean, it would be cheaper to make a monolithic wall, but there you need bricks like that to get some nice U values. My opinion and all what we found in the last years, it's far better to make a construction where you separate the static issue and maybe the thermal mass and the insulation. Put the insulation to the outside, the thermal mass to the inside, and this is also the static function. So separating it makes walls thinner with the same U value or with the same thickness, you get a far better U value. And then you have to look for, of course, thermal bridges and avoid them. You know, thermographic cameras. I don't go now here into too much detail, but showing you a bit about how thermal mass is working. Some of you have seen that picture maybe before. So I have a transient simulation of heat transfer with this partial differential equation. So we have a concrete wall of about 33 centimeters. That's a concrete wall. And I have a variation of 6-degree temperature over 24 hours. On one side, on the other side, I fix the temperature. And what we see is that the wall here at the outside doesn't get the maximum temperature because we have a U value, no, an alpha and heat transfer coefficient coming from the air to the wall. So here we have the highest temperature reduction. So the temperature variation even here on the outside is only by 2 degrees when the room has 6 degrees. And then, of course, to make the heat flowing inside, it needs a gradient, otherwise no heat flux. And to take the heat out, it needs also a gradient. So the temperature variation becomes smaller and smaller, and after 10 centimeters of wall thickness, it's not really seeable anymore. So thermal mass means a lot of area and not thickness to make it work. And there is no material. It's also quite important because sometimes people sell you shit, sorry, that the thermal mass and that the material can be thermal mass and insulation in the same time. But thermal mass, to get the heat inside as much as possible, it needs a high thermal conductivity. It needs also the high thermal conductivity means no air in there, no gas in there, because gas has a very low thermal conductivity. So that means a high density. And to store a lot of energy in one volume or 1 kilogram, we need a high CP. So this is thermal mass, high thermal conductivity, high density, high specific heat. An insulation material, well, it should not conduct the heat, so it should have a very low thermal conductivity. And to get this, it means a lot of gas in there. And if you take a fur of a sheep or a bear or whatever, that's the same thing. You have a lot of air with very little surroundings around, and that makes an insulation material. So there is no thing that is thermal mass and insulation material in the same way. Well, and this is a figure that shows you different materials with that density and their conductivity. Well, if you can cool down your building at night, then you can reduce by far the maximum temperatures in the room. So this graph shows you different constructions of the same building and different temperatures in this building. So, and as heavier the construction is, as more you cut down these temperature peaks. Everything is the same. It's the windows, it's everything. No change. So thermal mass is, if you have changing temperatures and if you can cool down the building at night, it's a very, very useful measure. But even if you cannot cool down the building at night, you can reduce the temperature peaks and then the peak power of the cooling machines. And you can size the cooling machines far smaller because they can run now for a longer time, and you can run them also at night, where also recooling temperature is lower, and pre-cool, let's say, all your thermal masses, so you start with lower temperatures during the day. So thermal mass helps you also in reducing investment cost. Well, then we come to the sun. My time is really running, so it's tricky, but I see how far I can come. Well, that's a solar position plot you should know from your country. And you see, well, in summer, you have very high, the sun is nearly 90 degrees above you. In winter, it's about 40 degrees. And out of this graph, you can derive in which direction should the windows face. What is the background behind? I mean, in summer, you don't want to have the sun in because it's hot anyway. And in winter, it would be nice to get some sun into your building because then you need to heat it less. So in what direction should the windows face? If you let them face to the east, well, what is happening? All the year, the sun is rising at the east, somewhere a bit more to the north and a bit more to the south, but the sun is shining in a very flat angle onto your window and you get all the sun in. And the same happens, so in the morning, the east windows get all the sun. And in winter, not in winter, and in west, and that's all the year. All the year you get a lot of, but you get even more in summer. Because in summer you have, the east is here. In winter, well, sun is already moving away from your side. And in west, you get the same thing, but in the afternoon. What is happening to the south side? In the south side, in winter, all the sun is shining all the day on the south, from to the south side in different angles, but it's in a low angle. So you have a very high projected area to the sun, so you get a lot of sun coming into your room. And in summer, your projecting angle is very very steep. So the projecting area to the sun becomes very small, so you get very little sun in. So in your climate, even more than in my climate, it's very good to face the windows to the south. And even without any overhang, they won't get a lot of sun. So here comes the orientation in there, and that's where I said with the first sketch of the building, you can very much have a very high impact on the energy demand for heating and cooling. Because here in the east side, you have in winter a bit less because the sun is already moving to the southern side, so away from my wall. And in summer, you get it full. So you have here in summer a lot of cooling demand, and in the east side and in the west side, and in winter far more heating demand than on the southern side. So this is very important for architecture, by the way. Well, and then we have different types of windows. These are 2- and 3-pane windows as we know them. I don't want to go here into detail because time is running. Well, you have also different ways of mounting it. So the best way is to mount it in that way that the window is within the insulation area layer, and here insulation is even taking over. So we have here, if you calculate thermal bridges, you come then get the best values, including the thermal bridges, if you do it that way. By the way, we had a passive house conference in China, where they also built large-scale passive houses, huge passive house settlements with 20 stories and about 20 buildings like that. And they trained their people on site how to do it in that way, and how to make other details in a passive house. So we were there on site, we came in and we saw every worker had to pass by and was introduced how to build up these details and why they are important. So that was the way the Chinese were dealing with this problem of unskilled workers. And I think that would be very good if we have it more around the world. Well, how to calculate that, I would keep it, but here again, the orientation, this is nothing very new with the sun, which I told you. So a single family house, a multi-family house, if it's facing to the south, you get all the sun in winter. Well, this is for my climate. In winter, it's a bit more steep. For you, it's 40 degrees here. But in summer, it comes even from the nearly 90 degrees, so you have no sun at all in there. And this is also not new. Also, old pueblos were built that way, so you can have a look back. Well, shading is a wide field. There are many different kinds of shading, but just one idea is, well, we said it should be possible to open the windows at night. And to make this possible, then, well, these shading should be burglar safe, and it should be safe for rain coming in. And not too many of these shadings allow it. I mean, this shading would be quite good because then if it's closed and even shut, then no burglar comes in. Also, these are quite good. But here, that's not really a burglar protection. And here, well, if you close it down, it's burglar protecting. But if you open the window behind, there are just 2 little holes in there that you get real ventilation. So these are things where you can think of. Well, I think my time has gone. I could tell a lot about renovation, maybe a very last picture of a nice example how you could do renovation. So if you have an old building, well, what they already did, which is not the optimum, but still quite good, that they, let's say, fixed a new heating system from the outside and made all the piping from the outside. And then they mounted very large tables, prefabricated tables, including the windows and insulation material and everything on this room. That means first it needs some technology. So first you have to do a laser scan of the whole facade just to get it really working, because it's never a completely straight area. It's always an old building. And also to avoid thermal bridges, they put the whole balcony also in prefabricated elements. They put it into the building site in it. There were other examples, but that's something we more and more try to use, is that we have these prefabricated elements for renovation systems. And finally, that was the same system, our renovated building in our university, which looked quite bad. I was from the 70s, was very bad, and we are now down to a very low energy demand. And in our climate possible, the whole building has no cooling machine inside. We cool down by opening the windows automatically in the night and then let the building cool down. Okay, sorry, I had far too many slides, but I want to finish now so that we get at least some discussion being run, because at 10:30 or 10 minutes about, I need to go to the rector. Thanks a lot for listening. And now I'm very interested in your questions. So I stop here my.
Well,
thank you very much.
Thank you, Professor, for your wonderful presentation for us. I think, do you have any question, participant? Since there is no any question received in the chat box, I'd like to move further for warping the session. Well, yeah, we got a chance to experience your ground stories from on the energy efficient building design, how we have to get the knowledge about the building physics, how we have to well understand about proper selection of the material, like as thermal mass, thermal lag, and thermal bridges, and with the proper knowledge of material and users behavior, climatic variations, and the proper fusion of engineers and architects, and well understanding of technology, we can set up an energy efficient building in Nepal, and we can design it. Though the climatic, due to the climate change in Nepal, is quite a challenging, but we do. Yes, with all this, now I'd like to invite our Professor Dr. Bim Prasad Shrestha for dropping his closing remarks. Well, we all know him as he is currently director of student welfare director, and a lead vice chancellor of Office of Global Engagement of Kathmandu University. Well, he is a team leader and principal investigator of IRDP project run by Korean government and Kathmandu University in Nepal. He has done his wonderful job and remarkable job in this COVID-19 period, that with supported of the NAST of the Nepal, with our final undergrad student in Kathmandu University, he is helping in making the conveyor belt for rubber band for transfer of COVID-19 dead bodies from mutuary to vehicle without any physical contact. That will help in supporting us. Well, now I request Professor Dr. Bim Prasad Shrestha for his remarks.
Hey, Chitis, thank you very much. So giving very instantaneous kind of opportunity for me to speak with all these distinguished guests. Especially, I do see a lot of friends and colleagues, and I saw this morning about the flyer that you prepared, and I would like more to be called as a faculty at a department, because this is a kind of a scenario that we work together with the students. Professor Wolfgang, especially, please accept a very sincere appreciation from Kathmandu University for accepting these invitations to highlight on some of your experience working in a energy efficient building design and its ground reality, that is one experience. In fact, I happen to be instructing these students, to prepare them for graduate seminar as a part of their graduate program. And the idea came up like, this is a very emerging, new and multidisciplinary scenario. Why do not we share with the several other institution and other fraternity who has been working in this sector. So this webinar series has been conducted, especially in the first day of the webinar that we invited our in-house expert, Professor Vivek, and his research team, then followed by some of the renowned architect from Nepal who has worked and who has also been working in Nepalese government sector. And the second webinar series, we work with some of the nationally renowned figures in designing the energy efficient building and practicing them, especially from Tribhuvan University and some of the practitioners. And today is the third day. I'm very delighted and glad that it has been almost like an international festival today. It presents our Professor Wolfgang, who has in fact, highlighted of his own experience in Europe. Especially talking about Austria, you are you are not Australia, I know, you are Austria, Central Europe, very, very central, very core heart of the center in Institute. I have not been, but I have been to your country. I've been to Switzerland and some other countries.
Okay.
And with the Finland, the UK, and other countries, we have been very closely working. Especially, we do have very good partnership with Norwegian University of Science and we have been very closely working, and Europe has been a very good instrumental for building, particularly in the engineering sector at Kathmandu University. And this collaboration, in fact, I do remember when your familiarity with our Professor Hari Neopane, when you talk, I do see that you had a couple of meetings before, very memorable meetings in past, and that is bringing us to start to make us this energy efficient building design course as a part of an academic endeavor here at Kathmandu University. At the moment, we are running this program as a multidisciplinary. The students are not only from mechanical engineering, they are from civil engineering, they are from, it's open for other engineering backgrounds as well. So that makes it a truly interdisciplinary kind of courses that we are running here at Kathmandu University. And of course, I wish, the students would have given you some more time seeing your slides and talking about a very new word, like sometimes when we say smart house, we normally think with some sort of gadgets and some sort of things. Yeah. But your way of defining smart house with the appropriate selection of the materials, because material science is another big area that we need to work on, where we really need to select appropriate material for thermal insulation or thermal energy savings or passive heating or passive cooling kind of scenario. So this is a really the interdisciplinary kind of topics that we need to work on. And especially you can see also our grad students, some are from civil engineering backgrounds, some are from mechanical background, and they are really working, even working in a classroom itself is a learning for them. And this kind of collaboration, this kind of webinar as a part of their graduation, I'm very honestly, I'm speaking, this is not something like a very national, international the program that we are conducting, but this is a kind of enlightening or keeping them in touch with the experts working in this sector, particularly through the webinar. In fact, we wanted to have this program organized physically, attending in Kathmandu itself, because a big festival is coming very soon, even though we are in this traumatic situation of COVID-19 for a last long time. And we suddenly now the Dasha is coming. Of course, the situation of COVID is not gone yet, but people are a little bit in a festive mood. And we want to create, all the time talking about this COVID is not sometimes good. So sometimes we want to talk something different other than what we really need to work on. So with this note, I really appreciate and thank especially the faculty member at Kathmandu University School of Engineering, Department of Mechanical Engineering. And they really put, the flag that you have put some 4 or 5 years with the support from European Union, the program that we started jointly in Kathmandu University and Tribhuvan University and Bhutan. Now the university has taken the ownership to start on its own, even in spite of not having the support from the EU at this moment. So this is something really challenging, and we are working.
Thank you so much.
We really don't want to miss the train. The good thing that we started, no matter from where it got started, we want to keep this speed on, and at least to make sure that the good endeavors that we started, we began sometime in past, must continue, even though we don't get some external support or something like that. So that's a spirit the leadership at the university is taking on. And some of the good things that has been implanted by our past leaders is also being continued with this spirit, with the values that has to have a positive impact in overall society and education arena. So with these few words, particularly you might be knowing it, these days there is Erasmus Day going on, 15, 16, 17. And I will also say that, well, this kind of collaboration, what the Erasmus or EU has funded and began at some few years back, now taking on its own. So it could be an example for other European member or European universities also to see that something, if the good thing begins, it continues. Yes. With these few words, I really thank Professor Wolfgang, Streicher, and we, as your wish to coming to Nepal and Kathmandu University will be fulfilled very soon. I guess this COVID will not be long time. We pray and we wish.
Yeah. Okay.
We know this is the first wave, second wave, third wave. We don't know how the waves are increasing, but we pray this thing will not remain for long, and we wish we will have a face-to-face and physical meeting in Kathmandu sometimes very soon in Nepal, and especially Dhulikhel area, you know, where the students are living. That would be the wonderful.
Sorry, I have to interrupt you because I have to go to my rector. Well, thank you very much for Tribhuvan University, Kathmandu University. I wish you all the best in Nepal, and hopefully you can also keep some contacts to the Bhutanese. I don't know, would be interesting to get some more stuff running. And thanks a lot again, and congratulations to these students organizing that stuff themselves. I'm really happy that you have here very active people in your university, and the students are so active. So thanks again. Thank you very much, and we keep in touch. Thank you very much. Bye-bye.
For your time, valuable time. We'll be in touch.
Yeah, absolutely.
Thank you. Namaste.
Okay,
namaste.
I also need to leave here.
Yeah. Okay, now I'd like to wrap up this session. Thank you so much, our participant and professors, teachers.
I need to leave also. I have another meeting here. So thank you,
Yes,
Chiti. I will have another meeting and I will be in touch with you after.
Thank you so much, sir, for all of our attendees and all of our professors. Thank you for attending this session. Thank you, sir.